Perhaps one of the big ones for insects is a phenomenon known as discontinuous gas exchange. Now, this doesn't occur in every single order of insects. You definitely have it in things like the beetles, so the Coleoptera, the Lepidoptera, so butterflies and moths. Definitely the Hymenoptera, your ants, bees, and wasps, they also do discontinuous gas exchange. Diptera, your flies, your fleas, your Neuroptera, your lacewing, your antlions, and some of your cockroaches, your Blattodea, they all at some stage can move towards what we call discontinuous gas exchange. And the way to think about discontinuous gas exchange, the latter part of this video will talk a little bit about hypotheses as to why this phenomenon evolved. But let me just go through the mechanics. And one way to do it is to think about it using this graph, right? So this graph shows carbon dioxide release. So imagine if your spiracles are closed, well, then you don't release any carbon dioxide, right? So you hold it in and concentration of carbon dioxide increases as oxygen levels deplete, right? So you, again, start building an internalized pressure. Now, then we have what is a flutter phase. Now, the flutter phase is basically opening and closing the spiracles in rapid succession, really, really fast. And in insects that go through discontinuous gas exchange, and if you work with really large moths, like an atlas moth, it can actually do discontinuous gas exchange, and you can actually see the spiracles in rapid succession opening and closing. Now, as you can see here, the little peaks represent little bursts of carbon dioxide that escape just as the spiracle opens, but not enough before the spiracle closes. So it's not a large exit or exodus of carbon dioxide, right? But you hold in at this phase, you must be wondering, oh, then why bother? Why don't you just let it breath out, right? Not quite, because what's happening here is the flutter phase. The consequence of the flutter phase is that tiny bits of carbon dioxide escape. But that's not the purpose of the flutter phase, because the purpose of the flutter phase is to allow, remember that we're completely oxygen depleted now because we've closed our spiracles for so long. So the flutter phase is to actually, the purpose is to actually let the oxygen back in just enough to meet the aerobic demands of the animal at that point in time. And then the open phase basically has a huge release of carbon dioxide, and then this pattern repeats, right? It goes back again to the closed phase, the flutter phase, and the open phase. Now, why this has evolved, we'll talk a little bit about it later, but mechanistically, I think it might be a bit of fun if you even tried it now, right? So if you held your breath, that is imagining the closed phase of the discontinuous gas exchange cycle. So if you hold your breath, eventually you'll get quite uncomfortable. And the reason for that is because you're still metabolizing, you're still using oxygen, and you're generating all this carbon dioxide. So carbon dioxide up, oxygen down. Then the flutter phase can be imagined as you taking really, 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 really short, sharp breaths, but the inhale is greater in duration than the exhale. So it'll be like, something like this. So you're actually getting more oxygen in, but less carbon dioxide, less exhale coming out. That's the flutter phase, right? And it'll make you feel comfortable for just a few seconds, but it will get to a point where you just want to go, and let all of that carbon dioxide out, right? So that's the open phase. So hopefully that's a nice way to think about this continuous gas exchange if you physically experience what perhaps an insect might be experiencing. Now, there are some hypotheses for discontinuous gas exchange, and there's very little work done in this space in terms of testing these hypotheses. And in many ways, I guess we'll never know. And I think in reality, all of them in a weird way apply, right? The evolution of this discontinuous gas exchange pattern, the very fact that even though not all insects do it, a good number of insects do it, there's a first most important feature of all the insects that do discontinuous gas exchange. You'll learn about metamorphosis in the next module, but the thing to note about the insects that undergo discontinuous gas exchange is that they're all holometabolous insects, meaning to say they undergo complete metamorphosis, which also implies that there will be a stage in their life where they actually go a little bit low in terms of their metabolic demand, because in the pupal stage, there is no need to focus your metabolism on physical activity. It really is focused on breaking down your body parts and reshaping it. So that perhaps might be something to consider when we think about how this continuous gas exchange has evolved. So for a very, very long time, the hygric hypothesis was placed forward. Now, the word hygric is in reference to moisture or humidity. And so one hypothesis for discontinuous gas exchange is to prevent water loss, respiratory water loss, evaporative water loss, right? And the tests that were done to show this was in tiny little Drosophila, so fruit flies, and Drosophila is so tiny and their metabolic demand is so high because they're constantly flying around, mating, looking for food, laying eggs. So their metabolic demand is consistently quite high. So continuous gas exchange makes a lot of sense for an animal with that kind of metabolic demand. But in experiments where the flies were exposed to drier conditions, they actually started exhibiting respiratory patterns similar to discontinuous gas exchange. So the hypothesis, the hygric hypothesis, came about because this DCG pattern would be exhibited by an insect exposed to dry conditions, and that insect would typically exhibit continuous gas exchange. So that's the evidence for that hypothesis. Now, another hypothesis is the canothic hypothesis or the canothic hygrid hypothesis, because there's a little bit of overlap with preventing of water loss. And the word chthonic here is in reference to the underworld, but really it is in reference to the conditions, the abiotic conditions of the underworld, which typically mean you have low oxygen levels, so animals that will experience hypoxia, or high carbon dioxide levels, so environments or animals that experience hypercapnia, or both. Right? So this was work done in harvester ants. They're quite cute ants in my opinion, although you probably don't want to be bitten by one of these things. And they of course, there's a huge network that is underground, and so deep and vast the network of their underground homes that they would typically be exposed to hypoxic and hypercapnic conditions, right? So the idea for discontinuous gas exchange is also as a response to the environment that they're living in. If you are already in an environment where you don't have access to oxygen typically, and there's dangerous levels of carbon dioxide, then being able to shut off your spiracles so that you can retain what oxygen you have, right? Do your thing underground, and then when you get to an environment that is a bit more oxygen rich, like outside of the nest, then you have a mechanism to flutter and open. Right, so that's another hypothesis, but of course, needless to say, also related to moisture and humidity, because underground those moisture levels could be variable. Now, another hypothesis is related to oxidative damage, right? Because any form of aerobic respiration, including in you and I, can result in the production of reactive oxygen species, and ROS, reactive oxygen species, are the things that cause oxidative damage, right? They damage your cells, they damage your DNA. So you don't want reactive oxygen species, right? That's why having a diet rich in antioxidants is deliberately to combat reactive oxygen species, right? So in insects that undergo a lot of aerobic respiration, there's also this risk, right? Any animal that is aerobic has a risk of accumulating too much reactive oxygen species, and then there will be cellular damage, oxidative damage to your cells, which is not ideal. So one hypothesis for discontinuous gas exchange is that this is a phenomenon to regulate the amount of reactive oxygen species that can develop, because DCG is a mechanism by which you prevent too much oxygen from being built up in your body, which is very unusual in the case of termites, because termites do not exhibit discontinuous gas exchange. Termites work very hard, their metabolic demands are very high, so termites actually use continuous gas exchange most frequently. And it's unusual that, or I guess the argument against this hypothesis is because that in termites, they undergo continuous gas exchange, yet they have a lot of symbionts, the bacteria that help them break down the cellulose and lignin that they consume are very oxygen sensitive, right? So this is the counter to this hypothesis. Now, the final hypothesis is the strolling arthropods hypothesis. This one is slightly a bit misleading, but the idea of strolling arthropods is that these are animals with very, very high metabolic demand because they're moving all the time, hence strolling. So they're constantly moving. Think of your bees, think of your ants, right? And by virtue of them moving around a lot and doing around and being exposed to the environment a lot, it is not uncommon for them to pick up dust, to pick up tracheal parasites. And so one hypothesis for discontinuous gas exchange is that this phenomenon of closing and then rapidly opening your spiracles in rapid succession is a mechanism to ensure that you don't accumulate parasites or dust that would otherwise block up your tracheal system. Okay, so for a very, very long time, this is perhaps one of the oldest hypotheses for discontinuous gas exchange that was debunked, because when an insect undergoes molting, they molt everything, including the tracheal lining, right? So there's a fresh cuticle. So basically, any dust or any parasites that are on the outside would also molt away, right? But very recently, though, there's been a study on honeybees that demonstrated something really unusual, and that is that in honeybees, if you undergo if you have a test, right, where you have bees that are with parasites and bees without parasites. So by parasites, I mean parasites of the tracheal system, and there are many parasites of bees, of course. And the bees that had parasites were actually less efficient than bees without. Now, that tells us that the parasites have a significant effect on the metabolic capacity of the individual. And at the final stage where a bee is a worker, they're never going to molt again. So this hypothesis is more recently attracted a bit more attention and perhaps going to be investigated a little bit further. But whatever, the evolutionary drivers of discontinuous gas exchange, clearly it is something useful given so many orders of insects do it, and it is a mechanism by which they respond to the environment, and allow for the maximal I guess, again, we're always after balance, right? So at the end of the day, something like discontinuous gas exchange allows the insect to prolong its energetic consumption, right? So that's a really, really cool phenomenon in insects.